My name is Stephen Wokes. I am the Chief Engineer at Astroscale UK. A little bit about me. I'm happy with Steve or Stephen, but not Stevie. Please don't call me Stevie, it makes me cringe every time. I have a BA in mathematics, an MA in astrodynamics, and a PhD in astrodynamics, okay? And after I did all that academic stuff, I've been working in the space industry since about 2008, but I did take 2 years out to write and release a computer game. I'm not actually here to talk about that, unfortunately. But what I am here to talk about is to tell you about Astroscale, who we are, what we do, and how we do it, okay? But I'm going to start and end with why we do it, okay? So, the problem. So this is a little animation done by AGI, and it shows the evolution of the space industry and satellites around Earth since it began back with Sputnik, okay? Now, as you can see, there's a gradual increase in entities that are orbiting the Earth, okay? And there is a color coding scheme here. So the green ones are active, the yellow are inactive, and the red are just debris. They're bits of stuff which has failed, okay? And you can see the steady progress through the years as more and more stuff has got launched. Now that's been driven by the commercial success and the useful application of space, but the downside is there's a lot of stuff up there now, and a lot of it's yellow or red, as in it's not doing anything, or it's bits of stuff that's been there. So yeah, so this is where we are today and where we're going to be in the next few years ahead. So the problem is real, okay? I'm going to move on to the next slide. I think this is going to finish. Let's stop. There we go. So yeah, is there a space debris problem? The short answer is yes. It's more complicated and nuanced than that, but if you want a quick answer, yeah, there is a problem. The graph from the video shows the growth of trackable objects in space, okay? And it reckons it's going to hit about 34,000 in the next year or two. But the problem is that's only half of the issue, or maybe less than half. So this is another set of graphics that have been created, okay? And this is shows everything that's greater than 10 centimeters in orbit about Earth. And the numbers are about the same, about 34,000 objects, okay? This stuff is trackable, okay? There's an estimate that between 1 centimeter and 10 centimeters, there's 900,000 objects in orbit around Earth. And less than a centimeter, they reckon there's about 128 million of them. Now, these are estimates. They can't track these things, okay? And I'm going to come on to that a bit later, but that's what the experts reckon is in orbit around Earth right now, okay? So the big issue with this is actually the small stuff. It's not the big stuff, okay? Objects below 10 centimeters are very difficult to track, and below 5 centimeters, they're almost impossible, okay? But despite their small size, these are lethal if they hit another satellite, okay? And the reason for this, and some of you may know this, is that they're moving very fast, okay? So I'm going to just do a very quick recap on orbits, okay, for those of you who don't have a background in the space industry, just to explain how orbits work. The best way to describe this is Newton's cannon. So Newton had this idea, if you sit a cannon on top of a high hill, let's say it's 1,000 kilometers high, and you fire a cannon, what happens, okay? So cannonballs normally fire at about 400 meters per second. I Googled that, I'm not a ballistics expert. This is what happens if you fire the cannon at about 2 kilometers per second. It doesn't change that much, it kind of drops down as you'd expect. If you fire about 6 kilometers per second, it looks like this. You get about an eighth of the way around the Earth. And now the curvature of the Earth is important. You can't just assume the Earth is flat for that calculation. You've got to take in the curvature of the Earth. If you increase that to 6.8 kilometers per second, you get about a quarter of the way around the Earth. At 7.1, you get exactly halfway around the Earth. And at the magic number of 7.35 kilometers, you get a perfect circular orbit, okay? Now, there's a few things to note here for those of you who are not familiar with orbits. The cannonball's always falling. It's always trying to get towards the center of the Earth. But the problem is the Earth's surface is dropping away at the same pace. So that falling down motion and the Earth's dropping away because of the curvature of Earth are in a perfect balance for a circular orbit, okay? For those of you who are gamers, like I am, this is the cannon, if it sat there, it would be a perfect self-kill. It would just shoot itself in the back. But if the cannon shot and then moved out the way, okay, the cannonball would stay in orbit forever, okay? Air drag eventually and other perturbations will affect it and maybe bring it down over hundreds of years. But essentially, the point is, once it's in orbit, it stays in orbit. It doesn't need anything to keep it up there. It just is falling forever, okay? And a small note, the speed to achieve that perfect circular orbit does change with the altitude, okay? If you're higher, it's slower. If your altitude is lower, you've got to go slightly faster. Okay, so that was a little crash course on orbits. So back to the problem. So in LEO, we've got these thousands and millions of pieces of debris, and they're buzzing around at around 7.5 kilometers per second in low Earth orbit, okay? So collisions between objects can be anything up to 15 kilometers per second. Now that is really quick, okay? And the energy associated with that is ginormous. I mean, I'm sure a lot of people understand the formula for kinetic energy. You square the velocity. 15 kilometers per second is ridiculously fast. If you think about the average cannonball going at 400 meters per second, this is about 40 times as fast as that. So it's huge, the energy involved in these things, okay? So this transforms small, tiny objects into anti-satellite weapons. It just completely shreds through and kills anything it hits, okay? That's why the small stuff is a problem. And there's some pictures which show the problem. So on the left here, this is a picture of a 1 centimeter aluminium sphere hitting an aluminium plate at the bottom at about 7 kilometers per second, okay? This was done in a laboratory or whatever. The little sphere you see there, oh, you can't see my mouse, sorry, but the sphere is not the one that hit it. I'm sure the one that hit it is kind of vaporized, okay? But another one's been put in so you can see the size of it. And that's a 13 centimeter aluminium plate. Now, we don't build spacecraft with shielding and plate mail like that, okay? We tend to build spacecraft to be as light as possible, okay? Because launch costs a lot of money and it's difficult to get stuff into orbit. So you'd need like 6-7 centimeters of aluminium to stand a chance to reflect that, and no spacecraft is designed like that. So that's the problem. It's going to tear straight through spacecraft. And on the right, this is a picture taken by Tim Peake, actually. This was a little crack that appeared on one of the windows on the International Space Station. And they reckon that was caused by something that was like a fraction of a millimeter, maybe a tenth or a hundredth of a millimeter in size, and it just went crack one day on the window. Tim Peake did talk about how one of the things he was worried about more than anything else was space debris, because it's a real problem. You can't see it coming, and then suddenly, boom, you get hit by something. So, in conclusion, the big problem is there's millions of untrackable small pieces of debris buzzing around, and any of them can take out satellites or, heaven forbid, a manned space mission. Now, as a slight counter to this, okay, because the space debris calculation and issue is complicated, there is a lot of space in space. So between 500 and 1,000 kilometers altitude, there's about 319 billion cubic kilometers of space, okay? And that's a lot, okay? So you've got 128 million things, but still you've got billions of cubic kilometers. What that means is that any given second, the chance of a collision happening is quite small. But the problem is this is getting worse and worse. And every time it hits something, it creates more debris particles. And the concern is this leads to, well, as is famously called the Kessler syndrome, where there's like a breakaway chain reaction, okay? There's one collision that creates 1,000 pieces of debris, and then they go on and they hit something else that creates another 1,000 pieces of debris. It gets out of control. Now, this isn't just theory. So the Wikipedia article, I love Wikipedia, on the article about satellite collision lists 6 such high-speed collisions that have happened already, okay? And the most famous of these was what happened back in 2009 when the US Iridium satellite collided with the dead Russian Cosmos satellite. So Iridium was around 550, Cosmos was around 950. There's some nice pictures here. So on the first one on the left is at the moment of the collision, and then 10 minutes later, and then 3 hours later, you can see the debris clouds starting to spread out. Within a few months, that was spread around the entire Earth, those debris clouds. And slightly depressingly, this year, 15 years after that collision happened, there's still 1,100 pieces of that collision still in orbit. Okay? That's a bit of a scary statistic. And to be clear, that's trackable items. They don't know the stuff that's not trackable. There's 1,000 trackable items from that one collision. Okay? So, Astroscale. So before I get into Astroscale proper, just one slide to give a little bit of background relevant history. So Kessler first wrote about the Kessler syndrome back in 1978. That's when he started thinking about this and people started to become aware. That was very early, given that the space industry only really kicked off in the 60s. He was thinking ahead. But by 2001, the US introduced the 25-year rule, which basically said that a LEO satellite should be designed such that it re-enters the Earth's atmosphere 25 years after it finishes its mission. And this was to try and counteract the problem of increased numbers of objects being just left dead in space. Satellites would be launched, they do their mission, and then they just die and they just sit there as debris. So the US led this charge, and this has been taken up by other regulators from around the world. Okay? And then in recent years, there's been a push to actually reduce this to 5 years, such that when you finish a satellite mission, you've got 5 years to bring it down. And that's what the most pushy regulators are charging for now. Now, about 2010, it was broadly accepted by the space community that there was a growing problem here. Okay? But it wasn't clear how to solve it. Regulation was undoubtedly part of the solution, and still is, to be honest, and in enforcing the new space actors to minimize their contribution to the problem. But on its own, that's not enough. So, in 2013, Astroscale CEO Nobu Okada formed the company. So Nobu, he'd attended several conferences, IAC to name some of the big ones, but a few other ones, where the subject of orbit debris was discussed, in papers, and people were theorizing around it, but no one was doing anything, and that frustrated him a little bit. So he set up the company. He was determined to actually tackle this head on, okay? So the remit of the company was to take active action, and this is the tagline, for safe and sustainable development of space for the benefit of future generations. That's what he wanted to do. And in the beginning, it was just him and someone else in Singapore. There was just 2 people. But we've grown a fair bit since then. So 11 years on, there's 500 plus people working in sites across 5 different countries now, all trying to address this and achieve Nobu's vision, okay? So what does Astroscale do? Okay, we've talked about the problem, but how are we going to actually address it? So there's a few different avenues we take to try and help on this issue, okay? So first of all, we want to provide a debris removal service for failed, prepared satellites. I'll get back to what that prepared means a bit later, okay? We also want to provide a debris removal service for historical, unprepared space objects, whether they're satellites or rocket bodies or things like that. We also engage actively with regulators to encourage more responsible use of space. At the beginning, when Nobu started back in 2013, that was a large part of what he was trying to do, was to try and get regulators to take firmer action and try and get people more aware of the problem. And we still do a lot of work in this area. It's still very important to us. Also, developing the legal and licensing framework to provide the services we're trying to do. So we're going to get on to in a minute what we do and what those services look like. But when we started going down this avenue, it became clear quite quickly that we weren't able to even legally do what we're trying to do. No one has set up the framework for launching a satellite to go grab something. No one had ever thought of that. So we spent a lot of time just going through the legal side of this in order for us to then actually be able to do our job and try and clear up the space. And we still, although the licensing side of it, some of them are sorted out, okay, there's still a lot of legal work that Astroscale does and still pushes us and still trying to push for policies and regulation. And also, we've developed a docking plate solution. So this is a docking plate which satellite operators can put on their craft, and it will then ease us, or someone else, because there are competitors. I'm not going to deny we have competitors, but it will make it easy for someone to go up and then service their satellite, okay? And I'm going to, again, come back to that later. And finally, we'd also provide life extension services. So when someone launches a satellite, we can actually try and get more out of that satellite by going up and maybe refueling it, or maybe moving it to a more favorable orbit such that it can continue to operate for a few years, and we can get more out of the things that are already up there, okay? So that's kind of the fronts which Astroscale fights the battle upon, okay? Now, in this presentation, I'm going to talk about those first two there, basically the debris removal services which we are bringing to market, okay? And from now on, I'm going to focus the discussion on LEO. So Astroscale operates in LEO and GEO, but for the ease of just trying to get through everything in an hour, I'm just going to focus on LEO from now on, okay? So LEO being low Earth orbit, sorry. In the space industry, we have a lot of acronyms, and if I say anything that, that you don't understand, please just catch me afterwards and I'll explain all the acronyms. I'll try and stay away from them as much as I can. Okay, but before I get into how we do this, a quick note on what we don't do, okay? We don't go after the small fragments, okay? Although I talked about earlier that they're the real problem, it's not technically or financially feasible to try and clear up 128 million sub-centimeter pieces of debris, even though they're the lethal things. It just doesn't make sense on many issues. It's difficult. One, you can't track them. So how you go after and hunt something where there's nothing from the ground to keep track of it, that's a real problem, okay? Instead, Astroscale focuses on removing the larger objects. We're trying to take out the source of the small debris problems and try and stop the chain reaction happening, okay? That's the approach we're taking. Yeah. Right, so the challenge, stroke mission. So this is what we're trying to do. So develop a system that can remove satellites and other non-fragmented space objects, so like rocket bodies and things like that, from low Earth orbit in a way that's commercially viable and legally licensable. So it's kind of a long sentence, but that tries to encapsulate in one line the services we're trying to bring to market, okay? This is challenging on many fronts, okay? First of all, technically, it's not easy to do this, and the rest of this presentation will explore that, okay? And we're going to go through that, okay? The commercial aspect is also really difficult, okay? The motivations for operators to clean up their dead satellite, there are motivations, sorry, but there needs to be stricter regulation to help force them to do that, rather than just do what, 20, 30 years ago, everyone just left stuff up in space, okay? So trying to close the business case is tough when people are used to, for decades in the past, not doing anything and not having to pay to clear up their stuff. So there's a whole battle going on there. And then legally, there's no precedent for the type of mission we're doing. Nothing came before us, and that raised a lot of challenges, and there were a lot of hurdles to overcome with our first mission, Alpha D. A lot of those have been cleared now, but not all of them. And going forward, we're diversifying into slightly different areas, and the licensing around that is not clear as well. So there's still a lot of work there. Anyway, a note about the clients, stroke customers. So who are our customers? Who are we engaging with? So they are varied, and we get discussions and engagements from various different entities from around the world. They fall roughly into two categories, okay? So first of all, you get the commercial satellite constellation operators. So Eutelsat OneWeb, Kuiper, people like that. Or their institutions. So European Space Agency, the Japanese Space Agency, NASA, people like that. There's some people who don't quite perfectly fit in those, but they're usually broadly in one of those two categories, okay? Regardless of their organization structure, they come to us because they've got a problem. They've got something which they own in space which they can't bring down and deorbit themselves, okay? And thus they came to our door. So why do they do this? Why are they going to pay us to do this as well? So there are a number of possible reasons. So one, their asset, which is sitting up there, okay, is at a high risk of being hit. Now, I've restricted the discussion to low Earth orbit, but even within low Earth orbit, there's different altitudes in low Earth orbit that are far more crowded than others, okay? So up at 1,000 kilometers, there's not that much sitting there. At 800 kilometers, there's a lot of stuff, okay? And there's different bands. If someone's happened to have, their satellites died in an area that's very congested, that's a problem. And they'll get collision warnings from NORAD, who track this stuff. And we've got a customer who's getting a collision warning every week, and they can't do anything about it because their satellite's dead. And every week they sit there and they're like, "Ooh, I hope that doesn't hit us." and to date, it hasn't, but that's a problem for them. So one, because they don't want to be, there's bad PR. If the debris event happens, that looks bad on them. Even though their thing's dead and declared dead, it still doesn't look good. But also, it makes it more difficult for them in the future to get launch licenses. And also, it might actually make the debris situation worse, which could affect their other satellites which are trying to operate in that same orbit, okay? If it's not in a busy area, it could also cause a problem for them. So if something's at the constellation altitude, and a lot of these constellations, they fly hundreds or thousands of satellites at the same altitude. If one or two or three of them die, that causes problems for themselves. They have to keep dodging out of the way of their own satellites, okay? And again, the pressure from the regulators. So if the regulators spot that a satellite operator has launched 1,000 satellites, so then 10 years later, 900 of them are still up there, they're going to get a lot of grief from those regulators, okay? Because the regulators are aware of this problem, and the risk is the regulators will refuse for them to be able to launch their replacement constellation. So they'll stop saying, no, you can't launch anything else. You've got to clear up your mess first before we allow you to launch anything else, okay? Okay, I promised I'd get back to this prepared versus unprepared satellites. So, satellite operators are starting to think ahead, okay? And they are now fitting their satellites with grapple fixtures, such as like a docking plate or something like that. And a good example of this, I'll come on to that in a minute. Having a standard interface for docking, it makes it easier for us, Astroscale, or some of our competitors to go and attach to them. If we know what the attachment point is going to be, it's not half the battle, but it's a large part of the battle, okay? And as an example of this, the OneWeb satellites, they are all equipped with grapple fixtures. So there's 660 of them there at the moment. They've all got grapple fixtures on them, okay? So they're thinking ahead. And the regulators going forward are getting more and more pushy on this point. So when people want to launch hundreds of thousands of satellites, the regulators are kind of expecting this. And there's been lots of discussions with Kuiper and Kepler and other people about this very issue. Now, the contrast to this is an unprepared client. So they don't have a docking plate or grapple fixture or anything on them. That makes it more difficult for us because we've got to work out, before we do anything else, where we're going to grab them, how we're going to grab them, where it's safe to grab them. And that means we've got to sit down with them and look through their computer-aided design, the CAD model, okay, and work out, what can we move in? Oh, we can't do that. There's an antenna in the way. And it takes time. And it might end up in us having to adapt our spacecraft. And that's going to cost them more money. Because if we have to keep changing the spacecraft for each different customer we go after like this, it makes the whole service more expensive, okay? So that's the difference between prepared and unprepared. We like prepared, it's easier for us. Okay, ConOps. So, I expect most of you don't know what ConOps is. Maybe some of you do. But don't worry, ConOps is the concept of operations. It's a standard space industry term. It basically means the plan for the mission, what you're going to do in the mission, okay? So I'm now going to talk you through the ConOps of one of our missions. And I'm going to talk you through each phase so you can see what we do and how we bring stuff down, okay? So this is what it roughly looks like. This is a generic ConOps. This isn't tied to any one particular mission, but this is broadly what we do, okay? So we launch, we commission the craft, we go up, we rendezvous with the craft, we inspect it, we capture it, we then lower it down beneath the ISS, and then we let it go, and then it burns up naturally. So that broadly is what we do. I'm going to go through each of these phases one at a time. Some of them are going to be very quick. Some of them are going to take me a few slides to get through because they're quite complicated, okay? Now, before we even launch, there is like a pre-step, which isn't even on this diagram. That's why I called it phase -1, okay? Ground-based inspection of the client. So when someone comes to us and says, we've got a problem, can you bring down our satellite? The first thing we've got to do is try and determine the state of that craft before we launch anything, okay? So we do this by a number of methods, but one of the things we classically do is we use ground-based imagery and radar to determine what the state of it is. So as a minimum, we want to estimate the tumble rate of the client. How quickly is it spinning, okay? Something spinning at 1 degree per second is a lot easier to dock to than it's going at 20 degrees per second, okay? It all comes down to rotational energy and things like that, but it is a serious issue. We have means of dealing with faster spinning clients, but it's more difficult, it's more complicated. You've got to slow it down first before you then go in and dock to it, and that takes time. We'd rather know about that before rather than we get up there and be surprised. Oh my God, it's spinning really quickly, okay? Additionally, anything about the physical state of the client really helps us. When the big picture, is it in one piece? that helps. And secondly, as another example, what's the final resting orientation of its solar panels? A lot of satellites have panels with 1 or 2 degrees of orientation. If we can tell from ground-based measurements or from data from the operators what those resting orientations are, it makes our job easier. And that may seem a little bit frivolous, but solar panels changing orientation changes the moment's inertia of the spacecraft and changes their air drag profile. And if you're operating in an altitude where air drag's an issue, that makes a difference, okay? And we need to take that into account on our models. And I'm going to come back to that later, okay? So we'll try and get this information out of the satellite owner, but we often use ground-based measurements as well and try and build as much a picture of the craft before we get into designing the mission, okay? Right, so assuming that goes good and all the ground-based measurements look okay, doesn't look like it's in 10 different pieces, the next phase is launch, okay? So Astroscale procures a launch vehicle. We don't launch spacecraft ourselves, okay? And we insert it into the orbit of the client we're going after, okay? Now, there are some complications even with this phase, okay? That's because, first and foremost, we don't decide the orbit that we go into. And most satellite designers, you choose an orbit when you're designing your mission, okay? And then you design your spacecraft around that orbit. You say it's going to be a sun-synchronous. I'm going to get into stuff maybe you don't understand. I don't have time to explain, sorry. But there's different types of orbits around the Earth. It's based largely upon the inclination of the orbit, okay? But that makes a difference to the thermal environment and the power environment that your satellite experiences. From our point of view, we don't have that privilege. We go wherever the customer is. Wherever the piece of debris is that needs servicing, we're like, okay, we've got to work in that environment now. So our services satellites have to be very flexible and almost work in any orbit. That's a bit tough, okay? That's slightly challenging, okay? Furthermore, the launch we choose has to align to where that piece of debris is, okay? We can't launch anywhere and then move across to it. We've got to be going to the right position. And from another point of view, also that position is moving constantly, okay? Now, most people, when they procure a launch, they say, I want to go to a sun-synchronous orbit with a 10:30 local time of ascending node. And the launch provider will say, yeah, we can do that. We've got 2 or 3 slots coming up in the next few years. We'll say, great, we'll take one of those. Launch done. For us, we're saying we need to go to where this thing is. Oh, and if you launch a month later, then we need to go to a slightly different position because its orbit's changed in that time. And almost on a weekly basis, we need to update with discussions to the launch vehicle where they're going to launch us, and it changes us. And launch vehicle providers aren't used to that. We've done this a couple of times, and it's caused a few headaches because they're not used to thinking in that way, okay? And what this drives to is often we need a dedicated launch. We need to be the guys saying where the launch vehicle's going. We can't share launches, okay? That makes the launch more expensive, but it's the only thing that kind of works with the mission that we're doing, okay? Right, phase 2. Commissioning and orbit matching, okay? So these phases are relatively simple. First, we commission the craft, which is just you turn everything on and make sure everything's still alive and it survived launch and everything's good. Great. Once that's done, we then use the propulsion system, which is normally electric propulsion because it's more efficient, okay, to raise our orbit and match to the orbit that the client is in, the client satellite, the piece of debris, okay? And the end goal of this is to land or end up about a few hundred kilometers behind it, but in the same orbit as the piece of debris, okay? Now that's not trivial, but it's not too difficult. This is the easy bit of the mission, okay? We just get roughly to where they are, okay? Phase 3, the rendezvous, okay? So in this phase, we want to arrive about 50 to 100 meters behind where the client is, okay? So we start this phase, we're 100 kilometers back, we're going to end up 50 to 100 meters behind them, okay? That's the objective. The problem is we don't know where the client is, okay? We have to assume it's electrically dead. Now, when we generally get called up to bring down debris, the thing's not alive, which we're going to get. Now, there may in the future be some rare cases where they've got a problem and they can't deorbit themselves, but they're still electrically alive and their GPS is still working and they can tell us where they are. That would make this phase so much easier, okay? But in general, that's not what happens. They come to us when their craft is dead electrically and they don't know where they are, okay? Now, ground-based space situational awareness providers track stuff. NORAD tracks everything that's in space, okay? But there's a lot of people out there who build upon what NORAD do, and they also do ground-based, imagery-based campaigns to get better resolution on where your target of interest actually is in orbit, okay? So that industry kind of exists a little bit, and we need that, okay? But it's not perfect, okay? And there are errors in the position, and those errors are around tens of meters in radial and cross-track and along track, okay? Now that doesn't sound bad, okay? But there is a problem, okay? So a little bit of math here, sorry. I know lots of people were afraid of maths, but sorry. So the period of a circular orbit, okay, is dictated by Kepler's third law, okay? So the time period is given by this formula, okay? Where r is the radius of your circular orbit. So as your circular orbit gets bigger, the time period increases. Okay. So if you're going after a client piece of debris, and it's sitting at 750 kilometers, if there's an error of 20 meters in that radius, okay, that changes the time period, okay? And it varies, I can't do this in my head, but this is what Excel says, it varies it by about a 20th of a second. So from 5989.142 to 5989.091. Now that doesn't sound like a lot, that's a fraction of a second it varies the time period for. But you've got to remember these things are traveling at 7.5 kilometers per second, okay? So if there's those two pieces of debris that start 20 meters apart, and then after one orbit, they get back, and this one's lagging by a 20th of a second, that actually means that it's a 20th of a second, but it's 20th of a second going at 7.5 kilometers per second, okay? And that works out that it's about 377 meters behind the other one. So after one orbit, you don't know where that thing is by nearly 400 meters, okay? Over a day, by about 5.4 kilometers, that's your uncertainty. And over a week, you got an error of like 38 kilometers. So that 20-meter difference over time makes a problem. And slight spoiler alert, it takes us longer than one orbit to get from 100 kilometers to 10 meters, okay? So if we could do it lightning fast, this wouldn't be a problem. But that doesn't happen. It takes us days to move in and do this rendezvous safely and carefully. And therefore, this is a problem. We don't know where it is, and therefore, it's a little bit of an issue. Yeah, I've talked through that point already, sorry. Okay, so we counter this issue by using safety ellipses, okay? So the idea is that you use the natural dynamics rather than forced motion. So you put it into this kind of trajectory, and then you don't have to keep it there, it naturally stays in there. And essentially you orbit around the trajectory of the other client. So you know roughly where the client is, you say, I think it's there, and you set up this relative motion around it, such that you stay behind where the client is, but you've got this funny kind of circular motion. Now the advantage of this is, and we size the safety ellipse based upon our uncertainty. So if we know the uncertainty is plus or minus 20 meters, we say, okay, the safety ellipse has got to be at least that in radius. Maybe we'll make it 100 meters, that safety ellipse, okay? That means if you get it wrong and you've misjudged where in that 20 meters it is, you'll drift past it, but you'll drift over the top of it. So your circle, I'll do that again. So your circle will just move over the top, and your satellite will just kind of pass by the client, and you won't cause a problem, okay? This is the way to use the dynamics naturally to help you, okay? So you don't know exactly where it is. You might be going too fast on your approach. You might be going too slow. But if you set up the safety ellipse, it doesn't matter to some extent. If you get it wrong, the worst thing that's going to happen is you're going to pass it by, and then you can come back and try again, okay? And that's what we do, okay? So once we've set up a safety ellipse and you watch, are we moving towards it? Are we moving away from it? And you adjust the safety ellipse. Once you think you've got it about right to where the client is, you want to move closer, so you lower the safety ellipse down. Was that visible? I'll do it again. It's a very, very small animation on that one. Okay. As you lowered your safety ellipse down, you've reduced your period, and so you'll naturally move forward. Okay? Still using the safety ellipse trick, okay? And we do this repeatedly, okay? Once you get to about 10 to 30 kilometers behind the client, you can start to pick it up with your onboard cameras. Now that distance depends greatly upon what you're tracking. If you're tracking the ISS, you'll pick it up from 100 kilometers. If you're tracking a small little like CubeSat thing, you need to get very close, okay? But at this kind of roughly, for our clients to date, between 10 and 30 kilometers, you start seeing on your cameras little specks. You start seeing a pixel or two of where the client is, okay? And you can use that, okay? So there's a technique which we use called angles on in navigation, okay? AON, another acronym, sorry, okay? And basically, you need to know where you are, you need to know your attitude, and where your camera thinks those pixels are that correspond to the client. And from that, you can reconstruct the orbit of the client, okay? Now, I'm not going to lie to you, this is quite complicated, okay? So don't worry, I'm not going to go into the maths of this. It's quite a messy process, okay? And it's only been used a handful of times in space before. 2 of those are our mission, okay? We're quite a pioneer on this, but we weren't the first to use this, okay? But this is the method we use, okay? We sit there in a safety ellipse behind it, and we look for those little pixels on the camera, and from that we determine where the client is, better than what we got from just getting ground-based measurements, okay? Once we've got there, okay, great, we know better where it is, maybe the area is now a few meters as opposed to 20 meters, we move in, and we keep reducing the size of the safety ellipse and moving in and getting better and better information, okay? So that was me shrinking the safety ellipse there. Okay, and then we move in, and you do this iteratively until you get to a point somewhere between half a kilometer and a kilometer, sometimes a little bit further, where your short-range sensors can pick it up, okay? Which for us in Astroscale to date has been a LiDAR system, okay? Which is like a radar, but it's with light, okay? At this point, your LiDAR is very accurate and it's very reliable, and you know exactly where it is with respect to where you are, okay? Once you've got it in your LiDAR system, you're great, and then you can move in much closer and move that, where we're trying to get to, 50 to 100 meters behind the client using your LiDAR-based system, okay, which is safe and reliable and gives you very accurate measurements, okay? And that's how we do rendezvous, okay? We've done this a couple of times. I'll come back to the end about groundbreaking nature of all this, but yeah, it's quite tricky. All right, a small quick aside, okay? So I'm not going to go into the equations of relative orbital motion, okay? But I want to give you some idea of how they're not intuitive, okay? And how it's all a bit weird, okay? So let's take an example, okay? Where the surface is sitting 10 kilometers behind the client, okay? They're buzzing around in perfectly the same orbit, okay? And you, in the surfacer, you thrust towards the client, okay? So your thruster plume goes in the opposite direction, but your delta V towards the client's location. Those of you who have some understanding of orbits, what happens is that pushes out the apogee, the other side of the orbit, okay? What that means, though, is that because the semi-major axis, or the mean radius of that orbit has increased, your period's increased. And as we talked about earlier, the period increasing means actually you drop backwards, okay? Which is very counterintuitive. You thrust towards the client, you end up moving away from it, okay? And it's all due to that Kepler's third law again, okay? So that makes moving around in relative orbits slightly weird, slightly confusing, okay? The bottom plot here shows the relative position, okay? This is what it would look from a relative point of view of the client being stationary. You'd kind of thrust towards it, you end up spiraling backwards like this every orbit, okay? Now, in 1965, when NASA first attempted a rendezvous in space, they failed horrendously because of this very issue. Those poor astronauts sitting in the spacecraft, thrusting towards the craft they're trying to rendezvous, they kept going backwards and saying, what's going on? And they were reporting down to NASA HQ, and no one understood relative orbits. A year later, they got it all sussed and they did their first successful rendezvous. But that just shows that this isn't obvious. And even the NASA guys, they didn't really understand this when they first tried to do this in orbit, okay? All right, that was just a quick aside. So, phase 4. Client inspection. So we've got to 50 to 100 meters behind the client, and we're sitting there. Great. We now need to look at it, okay? That may seem trivial, but actually this is really, really important, okay? Because sometimes we're asked to remove stuff that's been sitting up in space for decades, okay? And we don't know exactly what state it's in. In phase -1, we would have tried to use whatever ground-based measurements we had, but it's never going to compare to being up there, close and personal, take some pictures. Is it all in one piece, you know? That's a big question. Has it got chunks that have been knocked out of it, for example, okay? Has it suffered any damage that are going to affect our models? I talked about air drag earlier. In moments of inertia, another key one, okay? If half of the thing's missing, we're like, wait a minute, that's going to change the dynamics once we dock to it, okay? And critically, where we're planning to grab it, is that still in one piece? So if they've got a docking plate on there, Is it still attached? Or if we're trying to interface to the separation ring of the craft, has that been damaged? Because if that's been damaged, you've got a real problem, because you've designed your whole mission based upon grabbing it in a certain place. If you can't do that, then you need them to be very adaptable. And you might be able to recover it, but it's going to be very, very tricky, okay? So yeah, we need to take several pictures of it, and we then download them and we look at it carefully and we assess, okay, is it good to move forward, okay? Now, outcomes of this. Best scenario, the client craft is exactly how we thought it was going to be. Everything's as we intended. Great, full steam ahead, get on with the mission, okay? Middle-ish scenario, it's not quite what we thought it was, and we need to adjust some of our stuff, but we think we can still do this. That adjustment could be hours, it could be really that quick, it could be like, oh, the solar panels aren't quite what we thought, that changes the moment of inertia a little bit, update that, a few hours later, okay, we'll be good to go. Once we dock, we'll understand the moments of inertia, we can then control it. Great. But it could be more difficult than that. It could be part of it's missing. You know, a solar panel has been knocked off. Like, ooh, wait a minute. Or there's a bit of debris that's been hit and part of the antenna is now obscuring the docking plate or something like that. Stuff like that could take longer, okay? And then, of course, there's a worst scenario where there's no way we can dock with it, okay? So I've talked about, you know, that could be like the interface point is damaged. That's the obvious thing. There could be other things as well. It could be in such a damaged state, there could be stuff flapping around, and therefore the dynamics of the thing are fluid and dynamic. It's not a rigid body. That's going to cause chaos as well, okay? So there's a few different cases there. Hopefully, we're in the best case, or one of the better middle cases, okay? And then we proceed, okay? A slight aside before I get into the next phase. Inspection is so critical that some of our customers have said to us, actually, we want you to go up, launch a mission to just go look at it. Then we'll launch another mission to then go get it, okay? Because they don't want to commit sometimes tens of millions to bring down something which is big and awkward. If a little smaller mission, which costs 5-6 million or something like that, can go take a picture of it and say, oh, when it's not serviceable, don't waste your money sending up the big guys to go get it and bring it down, okay? So this has happened to us, and it's not uncommon, okay? This happened to us on the Astroscale mission. JAXA, the Japanese Space Agency, contracted Astroscale to inspect a 2-ton rocket body, which has been sitting up there for a couple of decades, with the intention then, if it all looks good, then launch a follow-on mission to grab it and bring it down, okay? So early this year, that's what we did, okay? So this is the pictures from our satellite. So on the right-hand side, you can see us getting to about 50 meters behind, a nice panoramic picture. And on the left, there's a nice close-up of the state of that rocket body. Now you can see, if you look closely, that it's not quite in perfect condition. There's these little strands coming out to the left or right, which are bits of metal which is broken off. Something's been hit there, and it's been knocked around a bit. But in general, it's in a good state. For sitting up there 15 odd years, I was surprised when I first saw these pictures when they came down that it's in such a good state, okay? So it's looking good. There is an animation here. So when we got up there, we sat behind it 50 meters. We then flew around it, okay? So we did several fly around it and took pictures as we were flying around it. Now, the rocket body itself isn't moving that much. Its tumble rate is very low because it's gravity gradient stabilized, okay? So we are literally moving around it, which you'll see in a second because the Earth's going to come into view any second now. There we go, okay? Now, we did this on 3 or 4 different axes because we wanted to inspect it from all the different angles, okay? And just check that we understood the state of that rocket body to help the next mission to then go and grab it, okay? So, yeah, that's what we did. So we've completed the inspection part of that mission. It's done, okay? Now, we might actually do some extra stuff with that mission, but the point is the reason why JAXA contracted us, we're done. We've done what we needed to do, okay? And off the back of that, Astroscale has now been awarded the follow-up mission to then go and grab that and bring it down, okay? So, which is great news for us as a company. We're very pleased with that, but this shows them the importance of a good inspection to then lead on to the mission to book the orbit stuff. Okay. Client capture, dancing. That may be a phrase you didn't expect to see coming to this, dancing, but yeah, it's very important to us. So assuming everything's gone fine so far and we're clear to proceed, what do we do next, okay? From here it gets even more complicated, okay? To attach the client at a known interface, you're going after a docking plate or something like that, you need to first synchronize to how it's tumbling. If the thing's not tumbling, it's perfectly stationary, it's a lot simpler. But usually it's got some tumble rate, okay? And you need to sync to that in order to then move in safely to grab it in the right place, okay? And it's tricky to do this because you need to watch it and predict where it's going to be to do that sync, okay? So there's some onboard intelligence and some ground-based intelligence as well. Essentially, the craft chooses when to sync to it. It watches the motion, it predicts how that tumble is going to evolve. It says, I think the best place to be is at this point, at this time, gets into position where it needs to then do that sync, okay? And then once it's synced, it then enters the dance phase, okay? So when the servicer is synced to the client that's tumbling, they kind of orbit each other around like this perfectly until you then move in and then grab it. Now, I've been doing this for 5 years, and that one slide makes total sense to me, but I thought it might be a little bit confusing to you guys. So what I've got now is a little animation, essentially, to try and make it a little bit more understandable, okay? This isn't in PowerPoint, though. This takes me back to my Blender days when I was writing computer games, okay? I love Blender, okay? So this is the little animation I put together. I'll set it running. Okay, so here we have the client, okay, which is tumbling, okay? It's a fairly, relatively slow tumble. What we're interested is in this point here. This is the docking interface which we're modeling, okay? Could be a docking plate, could be a grapple fixture, we don't care, okay? Over here we've got the servicer, which at the moment is just watching, okay? Now the servicer again has got some features, it's got a solar panel, but what we care about is the docking interface. What we want is this to align to the docking interface on the client perfectly. Now, at this point, it's watching, it's observing the client, and it's seeing how it's tumbling, okay? And then it just determines how to move to align. So about this point, it starts moving, hopefully. There we go. Okay, and it starts getting into position. It's predicted where the client's going to be at some point in the future, and it's moving its trajectory to align to it, okay? So in this case, it's moving down. The client's rotating round, okay? Let me get the view kind of right. And it's waiting for that perfect alignment between its docking interface and the client's docking interface. And when that happens, which happens in about 3 seconds, okay, it will then start the dance phase. And there'll be a little jerk, hopefully now. There we go. And now it's synced, okay? And now the two are perfectly aligned. So if you look from the client's perspective, it's perfectly aligned. If you look from the servicer's perspective, it's always pointing, okay? And they'll just continue like this. And this is the dance, okay? You're sitting there perfectly synchronized to the debris body you're trying to then move in and dock with, okay? That's what I was talking about on the previous slide. I just thought it might be easy to show you an animation rather than those bullets, okay? Right, back to the presentation. Sorry, there we go. So, once you've synchronized, you then begin the capture process. Now, this varies a little bit depending upon what you're grabbing and whether it's prepared or unprepared, okay? If it's unprepared, you'll need some sort of mechanical grabbing mechanism. If it's prepared, we can often use a magnetic system, okay? Because if the docking plates which we sell, they're magnetic in nature, and we can move in and grab them with a magnetic system that's much simpler, okay? So for a magnetic capture, all that happens is there's a slight extension of the capture system itself, but then we just reduce that distance whilst maintaining the dance until those 2 points interface, and then we magnetically grab the client. It's quite simple, okay? Well, quite simple. It's still quite difficult, but that's how we do it. For robotic capture, it varies, okay? It varies depending on your arm and depending on where you're grabbing the client, okay? Sometimes it might look quite similar to the magnetic capture. Sometimes we sync and then the arm does the rest. The arm extends out 5 meters and then does the grab because of the orientation of the client or something like that. It does vary. Either way, the guidance, navigation, and control, the GNC on board the craft, needs to maintain that sync throughout this whole time, and it needs to do it quite accurately, okay? Because when you come into docks or grab something, you generally need like centimeter level precision, which is quite tricky to do, okay? All right, another little aside, just very quickly. This is LCD, which we launched a while back, okay? But something to note is that during rendezvous, inspection, and capture phases, which I've just gone through, your servicer has got to be highly maneuverable, okay? It's got to be dancing around the client, okay? That dictates that you need chemical thrusters, and you need them on multiple sides of your craft, okay? A lot of spacecraft that are launched into LEO, they have like a chemical propulsion system, but it's got like 1 or 2 thrusters on the same side of the craft. we need thrusters all around our craft because we need that control authority on any axis, okay? And LCD on the right here had thrusters in each of the corners of its cuboid design, okay? On our later designs on LCD, we've got even more thrusters. They're not quite laid out the same way, but it's the same basic problem. You've got to have a lot of thrusters pointing in different directions, okay? That is also another slight problem because there's not a lot of satellite manufacturers out there who design and sell buses that have got that, okay? So again, today, Astroscale has had to design the structure of all our craft because we couldn't buy something off the market that had that capability, okay? Which is frustrating. I wish there was something. Once we've grabbed it, apart from having a celebration, a bit of champagne, okay, we then lower it down, okay? So there's a bit of detumbling it, we've got to get control of the attitude, and then we lower it down, okay? Now, for large clients, when we're going after big stuff, that could be quite difficult, because after docking, the center of gravity jumps, and the moments of inertia jump a lot, and that means your control system, which was fine when it was on its own, is now going to really struggle, okay? Sometimes we're going after stuff which is like 2, 3, 4 times the size of us, or even bigger sometimes, okay? That's the problem, okay? Once you've got attitude control, lowering the altitude, you just drop it down to the agreed drop-off altitude, okay? And that varies depending a little bit on the client you're going after. I'll go into that in a second. That phase itself isn't too difficult as long as the attitude is okay. The drop-off is always below the ISS, okay? We've never released debris above the ISS because that's a bad idea. That's the last thing we want to happen, is that something actually dropped off then endangers human life. That's not good, okay? It may, though, be a bit lower than that even still, okay? And I'll get onto that slide when I get to phase 8. The orbit lowering is usually performed by electric propulsion because it's more efficient. You get a lot more ISP out of an electric propulsion system, but it does depend upon the client, okay? Sometimes something's so big and difficult, sometimes it's just easier to do it quickly with chemical rather than use electric. It varies a little bit. Phase 7, we release it. So once we're at the drop-off altitude, we just let go of it and move away. This isn't too tricky, but at the moment of release, we've got to very quickly reconfigure our onboard system to say, you're now on your own. Because up until then, it's been dragging around something which is, like I said, 4 or 5 times bigger than it. As soon as you let go of it, your GNC needs to be very smart and say, okay, I've updated my moment of inertia matrix. I'm now not 2 tons. I'm now 500 kilos again. Now move away. So there's a very rapid handover there, which is a little bit tricky and stresses our GNC engineers out a little bit. But as long as you can do that transition quickly, you can then move away. And once you do that, the moving away isn't too tricky, okay? And in brackets, we probably will take a final few pictures of it. It's a sad moment. We've done our mission and we're saying goodbye to the piece of debris. And then phase 8, the client re-enters, okay? So the drop-off altitude is always chosen such that it re-enters the Earth's atmosphere within 5 years. We talked about earlier where 25 years was the norm in the past, but going forward, 5 years has been seen as more responsible. We want to be seen as more responsible, hence we always aim for that 5-year target, okay? That does mean it varies a little bit what altitude we drop it off based upon the client, okay? Sorry, I'm gonna go back and just talk about that a little bit. If a client's bigger, its ballistic coefficient is higher, and therefore you need to lower it off lower. If a client is small, its ballistic coefficient is less, and therefore it will be more affected by drag, and you can drop it off higher, okay? So that, we've got to adjust slightly each client where you drop it off to hit that 5-year mark. And then the client re-enters, okay? And it burns up on re-entry, as it was designed to do. And there is always a question about surviving fragments and what's the chance of it hitting anyone on Earth, okay? We only work with customers with these services where they've designed to come down in an uncontrolled manner. And that means they pose a very low, calculated risk to injuring anyone on the ground, okay? Any satellite that's designed to do an uncontrolled re-entry has to do this calculation to get a launch license, okay? So we haven't changed that. All we've done is we've gone and grabbed the thing because it can't bring itself down, lowered it down, and then we let go of it. And then it's back to being their thing, controlling in an uncontrolled way, okay? But we wouldn't do this for someone where there's an issue where it's well over that threshold, okay? That would be a serious issue for us, okay? And that's the ConOps. That's the different phases. Now, those of you who are slightly sharp-eyed may notice that on phase 8 here, the service has disappeared. The red box isn't there anymore. So what does the servicer do, okay, after you've let go of the client and it re-enters, okay? Well, often we go up and grab something else, okay? So we don't usually just do one piece of space debris removal, we do more than one. And that's tied to that commercial piece I talked about at the beginning. To get the best commercial value out of our customers, we want to be able to service more than one piece of space debris. That means we've got to do this multiple times, okay? So our poor little servicer is very busy and works very hard. Okay, I don't know how I'm doing on time, but I'm okay. So I've got a few final thoughts here. So our missions are technically challenging, okay? And we're doing things that have never been done before, okay? No one's ever sent an unmanned mission to dock with something that's dead and tumbling in space. It's never happened, okay? The US NASA guys have sent the shuttle up to service a few dead or dying things a couple of times. They serviced Hubble, as some of you will remember. But they've never done that with an unmanned cruise. It's not happened. So that's challenging. It's exciting, but it means there's no literature review to go from. There's no experience. We are working a lot of these things out the first time. That's tough, okay? We're trying to perform these missions on tight budgets and to make them within the financial expectations of our customers. That's tough, that's difficult. Now, some of our customers don't want to pay, but shock horror, we can't do this for free, okay? There is going to have to be a price, okay? But we have to be aware of their constraints. We can't say, we're going to develop a solution that costs 200 million to bring down a 10-kilo piece of space debris. That's not going to work. No one's going to pay for that, okay? So we work very hard to try and make our solution as commercially viable as we can. And we've always got that customer perspective in our mindset. We can't ignore this fact that they're being asked to pay money to clear up their mess, but we've got to keep that price as low as we can possibly safely do, okay? We can't ever jeopardize the safety, but we've got to be aware of that commercial aspect, okay? It's very important, okay? And finally, we're fighting to change the mindsets and regulations to ensure the people of this world can enjoy the benefits of the space industry. And that may sound a bit evangelical, but there's a lot of things we in the modern world take for granted. I mean, GPS satellites for driving cars around, for traveling on boats and planes across the oceans, they rely upon GPS. Comms systems that allow us to talk to people in remote locations all around the world using satellites. Meteorological services. I should have checked the meteorological service before coming here today. But this is very important. And it's not just about, again, shipping users of meteorological services critically, but it also saves lives. When there's hurricanes and typhoons coming in, if the meteorological services from space assets can give warnings to these places, they can take shelter and you can save people. There's lives on the line there. And there's other aspects as well of space. It's really important to our modern way of life, and we want to make sure that continues. We don't want to end up with a situation where in 10, 20 years' time, no, we can't do anything in space. It's just a big debris field. Oh, well, we're going to have to wait 1,000 years for it to clear itself up. That would be a tragedy, and we don't want that to happen, okay? So why do we do it? I said at the beginning I'd start and end with that point. Now, I've touched on that a little bit on the previous slide. It's important we protect the space industry and the things the space industry does for us as normal humans living on this planet, okay? But a thought does occur, it is difficult what we do. And personally, the people, me and my colleagues, we could find easier jobs out there doing something that's, well paid, but not quite as difficult as this. But that drive to look after space and to try and do a good job and set up the space industry for our descendants such that it's not a complete mess, that motivates it. And it gives us a kind of a moral and a purpose to our work. And that unites us across all the sites around around Astroscale and around the world. Each different site has a slightly different culture. As you can expect, the Japanese and the Americans have slightly different cultures from the English and the French. But we're all there for the same reason, to try and make the world a bit better and preserve the space environment, okay? And on a side note, that does actually really help us, because there are challenges, there are real difficulties, but when you're driving for a purpose in mind and you're trying to make the world better, it helps you get through those tough days and push through to the end result. So yeah, we do it because we care. So that is the end of my slides. I hope now you get an idea of what Astroscale is, who we are, what we do, and why we do it. Okay? Thank you.